All right, so here we are back. Let me load up the new content. The system seems to be working pretty decent. Load content. So we're going to take a look at hash tables, and then next time. So as I said, for those of you that might have joined late, um, there's only one lab this week. The lab will be sometime today. I'll post it perhaps tomorrow, and then you'll have until Friday to do it. There's 4 slide decks this week, so we're going to do 2 today and 2 on Wednesday. And probably also take a look at, in some of these slide decks, we'll take a look at some of the code that's being used to implement this, so you can have an idea how to do this in Java. All right, so hash tables. I don't know that. Let me double check something here. I don't know that we'll get through this entire thing. We might get about halfway or so. Let's see. Software engineering starts at 9:15. Okay, so we might. We'll see how far we get. So you see this first basic picture. Oh, what is going on here? This was not correct. Oh, there we go. Remove K, performance, cache tables. Okay, so we see the 0, 1, 2, 3, and 4. This looks like a basic array for the most part until you notice that there are little arrows coming out of the array positions, like 1, 2, and 4. And each one of those goes to some unique identifier, presumably like a social security number or something. So that's maybe like a employee lookup or something like that. Now, thinking back to the map ADT, that's very similar, because you've got this idea of you've got a key and a value, and this is what we just showed moments ago. You've got essentially the key being perhaps the array index position, and the value being the data that's stored there, like the social security number. So intuitively, map supports using keys as indices, such that m of k would be literally the key is that array index. So to get yourself sort of prepared for this, to wrap your head around it, think about a restricted setting where we'd have a map with n items using keys that are known to be integers in a range from 0 to n minus 1. So basically we're saying it's a map, except the keys have to be in a certain format in order for this to work, so that the keys have to be in the format of 0 to n minus 1. And if they are, then we can just use an array, and we can just stick those values in each array position. So like key at 1 is D, key at, the value of key at 1 is D, the value of the key at 3 is Z, and so on and so forth. So here's the key concept. We can't just use indices for everything we're going to do with what we're going to call a hash map, basically, because that would be really restrictive. Ultimately, we might want keys to be other things. We might want keys to be social security numbers, for that matter. We might want keys to be names. We might want keys to be URL addresses. We might, there's a ton of things we might want our keys to be. So what we're going to do is we're going to create what we call a hash function, which basically says, okay, I've got some thing that I care about, and I'm going to create a function on it that's going to return back a value that's going to be in that range. So if our range is 0 to n minus 1, like we see here in this slide, then our hash value that we get back from the hash function should be 0 to n minus 1. So then all a hash table really is a hash function that gives us back this. So for example, x mod n would be one example of a hash function where x is just some number, arbitrary number, basically any number, right? Because if you modulus it with n, you're going to get back something that's 0 to n minus 1. So, you modulus that, you take the modulo of x mod n, and then you've got the range that we care about, and that becomes our hash value for that key x. So then you could say that, well, a hash table ADT is basically just a hash function, like we talked about, like x mod n, for example, or some other hash function, because you can have other hash functions, right? You can have more complex things than x mod n, but that's a typical definition. You could, if you've got strings, you could take the ASCII values of those, for example, and, modulo that or something. I mean, you could take a string and you could get an integer value for it in a variety of ways, and that's your hash function. But the key is you have that hash function, and then you also have an array that you're storing these things in. So this stores entries such as social security number, name, where social security number is a 9-digit positive integer. And it's using the hash. Notice here they choose to use the last 4 digits of x as the hash function. And that's just their choice. They just basically said, okay, well, what's my hash function going to be? And in this case, it just takes the last 4 digits of the social security number, and bang, that's your hash function. So pretty basic there. Here we've got the hash code showing the keys go to the integer. And the integers go to our social security number. I kind of paused for a second there while I was reading that, because I was like, well, the thing about that is they're calling it a compression function, where really, you've got your hash value, or your hash key, which is, for example, here it's 1 because the last 4 digits are 1. Here it's 2 because the last 4 are 2. 9998 because the last 4 are 998. And they're saying use some kind of compression function. Well, this is the first time they're introducing that term, compression function. What do they mean by that? That's really this compression function here. That's the first time you've seen that term. That's really basically just saying that is how you get back the value. Because you need to take that, you could have another layer of abstraction. You could basically say, well, I'm going to get the hash code, and then from that hash code, I'm going to get what the value is. That step of getting the value out is basically dehashing it. It's taking that value and getting it out of the data structure. And that's why they call that compression. Now, what we're really trying to do here is the goal of the hash function is to disperse the keys in an apparently random way. So what we're really trying to do is we're trying to get the keys and the values into the data structure in some way that we can actually store them. So what are typical hash codes? Well, as I said, they don't have to literally just be, last 4 digits of a security or whatever. That's kind of a cheap way to go about it. They can be memory addresses. They can be integer casts, such that you reinterpret the bits of the key as an integer. That's basically what I meant before, where I said you can take a, you can take a character or a short or something, and you've got your key value pair, or at least your key. They can be component sums. So various bits of the key can be broken up into components, and those components we can sum those, and that can give us our hash code. So there's a lot of different ways of getting hash codes. Polynomial accumulation. You can throw a polynomial on it. You can basically say, okay, well, bit 0 is going to have some scalar on it, like z. Bit 2 is going to have a z squared. You basically say, okay, and some of this gets into like secure hash codes and things like that. You don't want your hash code to be just plain necessarily. It makes it easier to hack. So a lot of times people use things like polynomial accumulation to make a slightly more secure hash code that goes into the map, into the hash map, or the hash array like we're talking about here today. And you can evaluate these polynomials in O of n time. There's a mathematical thing called Horner's rule, which tells us that basically we can do that computation in O of n time and get out what the actual converted hash value is. So for compression functions, this is what I meant by, okay, you've got your hash function and then you've got your compression. So here we see that y mod n is the size of the hash table. It's going to be some prime number. Reasons for that basically get into some math theory so that we know that we've got dispersal and that we know that we've got something that we can actually hash out in the compression function, but that gets into some math stuff that really isn't for this course. Other things you can do is you can multiply, add, and divide. All of these, remember, compression, all the compression does is, let's go back a couple slides so that I remind you again what we're really doing here. We're essentially just saying we've got our integers that we took, and now we're going to those array positions. That's all compression is. So you could do that differently. You could get your hashed location from some combination of multiply, add, and divide. So a of y, or y is some scalar plus b mod n. And then you get a different position inside of the array that is responsible for storing that key for that particular hashed value. What I'm going to do is I'll go down to, well, we'll get through most of this today, I think, but then it looks like we probably won't get through the whole hash thing today. We'll probably start that on Wednesday. So an abstract hash map in Java here is basically saying, okay, it's an abstract map, so it's just a map. This was sort of the second version of showing you how hashes work, because the first one we showed you like a hash table, basically. We showed you a hash table. So this is now a hash map. So a hash map basically says, okay, we're going to take the map that we talked about last time, and we're going to make it into a hash map. And so it's combining these two concepts. I think a good way to do that is to look at how we would actually code it up. So notice that we've got extending abstract map kv, so there's the key and the value. We've got capacity being set, a random being set, various things being set inside the constructor. A lot of times there'll be some seed value, like that's our default prime that's being set, and that's going to be used for later when we compute the compression. We say get returns the bucket get, remove returns bucket remove. So bucket get, bucket remove are the internal structures of the hash map that we need to do. Put is going to do bucket put. Hash value, this is what they decide for their hash value. Math.abs of the hash code times some scalar plus a shift modded by their prime, which is basically their if you think of this similar to the array situation we looked at before, that's basically going to be their number of unique elements that they choose, modded by their capacity, which is basically a modifier on the prime. So your true capacity is going to be here, and your max is going to be in your prime. Then we have a resize method, bucket get, bucket remove, which we'll take a look at in a little bit. I think the idea here is that before we look at bucket get, bucket remove in code, we want to think a little bit about a few more concepts. We're kind of not ready to look at those yet. Those concepts are mostly collision handling, because what happens, for example, when you get to a position that already has an element in a hash map, instead of like in a regular map like we dealt with before, we'll do something like chaining to handle that. All right. Well, I want to allow a little bit of time before we have a 9:15 start for software engineering, and I need to get the slides together. I don't want to start that one late like I did today. With this one was a little running late, but that's because it was the first one. So hopefully the following ones won't be late. But anyway, this one did start late today, so if you got here and we weren't ready yet, you'll see those on YouTube. I'm going to post those very soon here, and I'm going to stop this recording for now. But before I do that, I want to ask, feel free to shout out questions in the talk channel. I think you all have voice mics. Haven't heard anyone yet, or the chat would work too. So again, you won't be asked to do too much with this stuff until I get that assignment made, that lab assignment that'll be due Friday, and there's only going to be one lab this week. And I'll get that made sometime today, maybe tomorrow at the very latest. But hopefully you're getting a good feeling for this stuff at the high level. I realize there might be questions once you start implementing, and that's why I think that what I intend to do on Wednesday is finish this hash map up. Then there's one other slide deck, the fourth slide deck. Some of these slide decks I don't always cover, but I'll post it anyway. It's just sometimes there's content in here that's goes a little bit beyond like skip lists. I'm probably just gonna I'm gonna skip lists, but I'll post it, and so we'll talk about hash tables and sets on Wednesday, and then you can start implementing them, and I'll stay online. And if you have any questions, you can ask me. I'll just leave the chat window open. So hopefully you get a start on that before then, though, and maybe you can bring your questions if you have any on Wednesday, because I'll try to post that lab assignment today or tomorrow. All right, well, I'm not seeing any questions, so guess we're good to go. I got about another 10 minutes before the start of the next one, so I'm gonna end this here and post these two. And for those of you in software engineering, we'll see you in about 10 minutes.